I'll start with this. Imagine you have a source of light shining against a screen with two slits. Now, for the pedants in the audience, this source of light has to be monochromatic light, light of a particular wavelength, whereas, of course, a light bulb is white light, and that's made up of all the colors of the spectrum, lots of different wavelengths. But imagine this is just a single wavelength of light, and you can see the light is coming out in waves like ripples in a pond. That's the nature of wave-like behavior. As the light hits the screen, it squeezes through the two slits, and each slit in turn on the other side becomes almost like a new source of light, and the light spreads out, it diffracts. And as the waves of light overlap, they will interfere with each other. So where a crest hits a trough, they will cancel. Where a crest hits a crest, they will amplify, and so on. And so on the back screen, you end up with what's called an interference pattern. What if we do the same experiment with atoms? Well, so imagine we have an atom gun, something that can fire atoms, a stream of atoms. You can't see them because they're very small. Let's block off one of the two slits. So these two slits are the dimensions and separation of the slits is chosen appropriately to show us how atoms do things. And so far, so good. Nothing strange here. You'll see a lot of atoms hitting the back screen. So this will now have to be some sort of photosensitive screen whereby when an atom hits it, it'll give off a little flash of light to say the atom has arrived here. The first mystery of quantum mechanics comes when we open the second slit. Because now we see something that's very much like the interference pattern we got with light. Rather than having two bands of spots where the atoms have gone through the two slits, it's as though the atoms have gone through the slits behaving like waves. And you get interference of the waves, and you get these bands. What if we were to not send the atoms all through at once, but send them through one at a time? Leave enough of a gap for the atom to get through to hit the screen. Of course, as I say, some atoms will hit the first screen and not get through, but those that get through will hit the back screen. So let's run the experiment again slowly. And gradually you'll see, as the atoms go through, they'll look like they're just randomly arriving on the other side. You keep sending atoms through one at a time, and gradually that same pattern appears. Well, we can try and be even cleverer. What if we were to spy on the atom and see where it goes? We can gently just observe which slit it goes through. So you put a detector just above the upper slit that will flash or beep whenever it sees an atom go through that top slit. Sure enough, you fire the atoms through one at a time. 50% of the time, the detector will beep. The other 50% of the time it doesn't, the assumption being that the atom has gone through the lower slit. But of course, I've been cheeky here. I haven't shown you the results of the experiment. That's what you get. But that's a different result to what we had earlier. So here's the last bit of sneakiness that we can play with atoms. Surely now, we're going to get to grips with it. Leave the detector there, but just very quietly go and unplug it. Don't let the atoms know that you're not spying on them. Make them think that you're still detecting them. So, yeah, okay, we're going to run the experiment. Atoms, okay, get ready, one at a time. We're going to be checking on you. All right, so run the experiment again. Now, if you can explain this using common sense and logic, do let me know, because there's a Nobel Prize for you.